going to do today is, as I told you before, the whole purpose of this lectures, this course or this lecture series is not as much as to teach you few things, but also that I wanted to learn few more things, few more tricks, and so I have just chosen a few set of things which interest me personally. So this lecture is not going to be very smooth as in general it should be, because there are still a lot of things which I'm still trying to figure out myself, and so you are free and open to budge in and suggest whatever you want to tell about it. So the theorem which I want to prove first is what is called K by click is W1 hard. Okay, so that is a basic goal which is going to be. And another thing, someone needs to make lecture notes. Like this is absolutely, whether this is an absolutely important aspect that someone. So you have to pair up yourself to, and after every 1 week, I need that lecture note. Like there's no more, and I like to go through it. Okay. Okay. Huh? Okay, fine. Okay, so what I want to show that K by click is W1 hard. But what is by click? By click is basically a complete bipartite graph, right? So when I use the word K T comma T, it means a complete bipartite graph on T vertex here and T vertex here and T vertex here. Now this problem is quite close to the click, but it was embarrassingly open for many years whether this problem is W1 hard, because it sounds so much more like a click than any other problem, but this problem was open, and almost every IPEC we used to get couple of articles who would claim, but there will be some flaw or mistake. And finally in SODA 2015 this problem was shown to be W1 hard, and this also got best SODA paper award as well as best student SODA paper award. Okay, so this is a history about this problem. Okay, and so we are just trying to go, we are just going to build up how the proof will come out and how things will work out, and it's quite different than you will see in the article which is currently available on the on archive, but so be it. So for example, let's try to understand when we try to give a W1 hardness reduction, say from click to dominating set. Okay, so I have a reduction from click to, so what, okay, so basically what I'm going to show you is that when input is a bipartite graph, then and a parameter k, testing whether this graph contains a biclick k comma k is W1 hard. That's what we're going to show. Okay. So suppose for now that whenever you make a reduction from say click to dominating set, okay, let's try to understand what we actually end up proving. Okay, so basically we will have an instance of G comma K, and we create an instance G star K star of G star K star of dominating set, and actually show that G has a K click if and only if G star has a dominating set of size subsize at most k. Agreed?
K star, yeah.
Size. Okay, thanks. Right, this is what we show. Now let's try to dissect this and try to see what actually it tells us. Okay, so basically forward direction when we show, we actually show this G has a K click implies there exists a set S subset of Vg star of size at most k such that n of s, right, is equal to V star. So this is what we show. Now let's assume the other way. What we say, oh, now if it has a dominating set of size at most k, then it has a k clique. But let's say G does not have a k sized clique. Clearly, if a graph does not have a k size clique, then it does not have a larger size clique, right? What does that imply?
That should imply, because of that, the smallest size dominating set is at least k plus 1.
So
G star, k star plus 1.
So what does they say? For all set S Vg star mod S less than equal to k, right?
N of n inclusive root is not equal to properly contained.
Vg star. Right? So if you are familiar with approximation world or PCP, this part is called soundness and this part is called completeness. Okay, and the idea of basic showing an approximation hardness or any hardness, for example, is that basically you are able to distinguish between what? So when you give this reduction, you are able to distinguish between graphs that contains a k size clique and the graphs who does not contain a k size clique, right? So basically here is a world, here is all this could be yes instance for G comma k minus 1 for the clique, and here there is a world of all the yes instance of G comma k. Now basically this reduction differentiates between here and here, right? So any hardness reduction must distinguish between this. Now the question is, when we show an approximation hardness, the whole goal is when we try to show this, we try to create some gap. You say, hey, when I'm yes, when it is a yes, then I have a solution of this large size. But when I'm no, I do not even have a solution of this small size. So basically you create a gap in the sense that when I'm no, I'm really very bad, but when I'm yes, I'm really very, very yes, right? So for example, when the people show that, so then the gap between if it is yes, what it is, and if it is no, what it is not, the fraction between them is what is called hardness of approximation, and that is a ratio which you cannot, you cannot get it unless whatever the assumption, the problem, initial problem you start with. Okay, now, yes.
Where are you saying this gap should be?
Here, like, so imagine yourself. For example, if I told you that G has a k clique, implies there exists a set S of size at most k such that this happens. Okay, G does not have a k clique for all S of size 1000k, this property does not happen. So now I have created a gap between, so like if it is yes, then I am able to find it yes, but if my instance is a no, then even 1000k size solution is not okay for me, right? So here I have created a gap between when it is yes, I do have a k size solution, but when I'm no, I'm really very badly no. It's not that it might have a k plus 1 size solution. Actually, it does not have solution of size up to 100k, 1000k. So if you are able to show such kind of reduction, then you will be immediately able to prove that because if G does not have a constant factor approximation or say 100 factor 100 approximation, you should be able to relate and say dominating set also does not have a factor 100 approximation, because if it is had, then I will do something here, get an approximation and do something good about this, right? So this is how you create gaps. Okay, now generally in parameterized complexity or whenever we show NP hardness reduction, the gap is between k and k plus 1, n or n plus 1 or whatever number you give, right? In approximation, it's a gap is between what you start from and what is the approximation factor you are looking for. So you try to create gap between those two in your instance creation. Now this idea is quite prevalent in all forms of reductions and everything, but The reason why I am introducing it this way, because very soon we will take the ideas from this lecture and try to show that dominating set actually does not have any constant factor approximation in FPT time. Like for any constant C, any f of k poly n, that does not exist this. So that is the whole idea. But first, the construction which we will do, the gap creating construction, right? So basically what I wanted to emphasize on, that whenever you make any reduction, you are actually creating a gap between yes and a no. This is always true. Okay, so that's a point number 2 which I want to know. Okay, so with that philosophy in mind, I'm not saying this is what we'll do. Now we will jump directly into k by click and see what kind of object we need to create here and how will we create those objects to show certain hardness. Okay. Okay, so what I'm going to define a property which, so I'm going to rub this part for now because this was just for the motivation, and let's see So suppose I have a bipartite graph, right? I have a bipartite graph, and if it has a k click, if it has say k a comma b complete bipartite graph, what does it mean? There is a set S of size A, there is some set X of size B, and then a complete this. But what also it means that all these guys, if I look at this set X, where does this set X belongs to? So I will introduce a notion and you will see why this notion is important, is that look at for all S in S, right, let's look at intersection of NS, okay, S in S, right, so it's a common intersection. What is the property? This common intersection contains our X. If there has to have a complete bipartite graph between S and X, then look, because look, everybody of this is neighbor to this guy, everybody of this is neighbor to the other guy, so in particular they are in the common intersection of the neighborhood, right. So actually finding a complete bipartite subgraph is about certain kind of neighborhood intersection, and that is what, yes, maybe not. I mean, if we are, it is possible that it is much larger, but you were only interested in a B size subject. But I'm not interested at this point of time, right? I'm only interested in B because maybe it is bigger, my running time could go too much to look into those kind of things. So we do not want to do this.
So is that Sx, that subgraph has to be an induced subgraph or just a subgraph which is a complete bipartite graph that is?
No, I didn't get your question.
No, so the problem in the problem definition, what is the definition? That
input is a bipartite graph.
Oh, input itself also is a
bipartite graph. I told you, right? The input is a bipartite graph, right? Okay, so input is a bipartite graph and the number k. Question is, does G has k comma k? Okay, fine. So let's introduce a sum symbol for this object. Okay, so for a S subset of Vg, okay, I will denote gamma of S as basically S in S neighborhood of S. Okay, so this will be the notation which will be huge, which basically tells the common intersection of all these people. Okay, fine. So this will be important. Now let me introduce a most important and critical concept of what I call, so this is the definition A star, which I will come back and modify. Okay, let me call it definition A star. Okay, I'm going to call it NKLH. I think it is called NKLH. Yes, strong threshold property. Okay, so I'm going to define a notion of NKLH strong threshold property. Okay, so we'll say a bipartite graph G A union B comma E. Okay, somehow he uses T, so let's stick to T maybe for symbolic reason. Okay, so let's say, let me rub this. This is not correct. Okay. So for every NKLH with, I will fix something. For every NKL, a bipartite graph T A union B comma E. Okay, T A union B comma E satisfies, let's call it strong threshold property if the following happens. What is this? That for every x in A choose, do you know the symbol A choose k plus 1? All subsets of size k plus 1 of A. NKLH, and I will tell you the property between L and H in a moment. Okay, basically with H is more than this. For all x in AK plus 1, okay, their common intersection is bounded by L. Right? So if you give me any x of size k plus 1, their neighborhood is, their common intersection is bounded by L. Okay. And what is a T2? For all x in A, K, their common neighborhood is at least H. Right? So this is the two property. So this is what. So now you see what I'm trying to differentiate. So if I'm looking at a set of size k, then they have lots of common neighbor. Whatever that lots of common neighbor will be quantified by H. But even if I just take k plus 1, right, the common neighborhood drops to at most L. Right? So this is what is a gap I'm trying to create, and this is the construction. So suppose we did have for every NKLH, right, we could construct such a bipartite graph with such a property, then can we show this theorem? Right? Like if we have such a nice construction of bipartite graph, then is it possible for us to show that k by click is W1 hard?
N is the number of vertices of the whole graph.
Yes.
Okay.
You will see what n is. Okay. Okay. So now let me write. Yes. There's no relation. Yes.
So if I pick two sets which are of cardinality k plus 1,
Okay.
I know their intersection is at most L.
Yes.
Right? I just randomly throw two elements which are not in their intersection.
So
Now their intersection
can grow. Of course. More and more sets take intersection, but the intersection can only decrease. Draw three sets, not three balls. Look at, draw two balls, two which intersect.
I thought we pick N.
Okay. Now this is not what we will use, but let's have this for now. And let me write another lemma, which is not what we will use, okay? But still, it's a good for the learning experience. So a lemma which it is, okay? So the lemma which is, okay, let me use my fancy iPad. Let k comma n be n plus and s equal to k choose 2. So by the way, this is the only reduction of the whole object which I'll give. I mean, probably if at all we'll see, this is the only reduction which is there. Everything is all about constructing such family of graph. So the reduction is very simple. Okay. Okay. Given a n vertex graph G and a bipartite so you see T and a bipartite graph satisfying N, K, L, H strong threshold property STP. Okay. We can construct a new graph, a bipartite graph let's call it does it need a name? I don't know for now. It doesn't need any name. Okay, a bipartite graph T. Okay, it doesn't need a less. Give it a name. Et. Okay, E. Construct a new graph H in polynomial theorem such that some nice property happens. Now you will see similarity to how we make reduction H1. If G contains a K click, then there exists X in L choose K, not K, L choose S. Okay.
Gamma.
Okay. Suppose I'm able to make this, I'm able to construct a graph H with this property, right? Now suppose, first of all, I'm talking about a very strong property, and then given that G, I'm able to construct a very strong graph called H. Now suppose if we had this property, using this property you were able to construct this lemma, prove this, then can we show that by click is W1 hard, starting from click.
What is the gamma HX? Gamma X means this neighborhood of X. Okay, intersection H.
No, I'm talking down in the graph H, because there are lots of graph floating around.
Okay, fine.
What is the role of T there?
Where is T? So look, G is your input graph, which is bipartite graph, because no, G is not bipartite graph because it will be an instance of a click, right? Now what I'm saying that, okay, if you have an instance of a click and I have a threshold bipartite graph, I'll construct another graph which is H, which has these properties. So like role of T is in the construction of H, because H has to satisfy certain beautiful properties. Right? How, like, given a graph, you only gave me G comma K, but I am returning you H, which is a bipartite graph and has certain set of properties. Right? How am I going to construct that graph? So to construct that graph, I will take somehow this your graph G, take my nice bipartite graph which has threshold property, and somehow superimpose them in a way that it satisfies properties H1 and H2.
There is the input.
There's nothing. So this is a lemma which takes a number K, a graph G, and produces a graph which has these properties.
It takes G and T.
Yes, it takes G, it takes T, and certain numbers. Okay.
And let's say H, construction of H will use T.
Construction of
H
will
use T.
T and G. Okay, we will see today. We will see. But suppose if this lemma is a black box, because this is not what we will need. We will need a much slightly weakening of this strength. This is too strong to be able to derive something. Okay, but I'm telling you that if I give you this, then the reduction from click to biclick is trivial.
Condition H1 and H2 don't use anything but T. So the lemma consequence, whatever.
Yes, I mean,
Okay, so H will use is what you're saying.
yes,
H,
right, because H has all this nice property, T has all this nice property.
maybe H you can write is a function
Okay,
of
T
G.
has some nice property. Okay, so H is a function of T.
H is a function of G. That's what I say, right? If takes this, we can construct this graph in polynomial time, so the such property happens. So it does take as an input graph G, the nice bipartite graph T, and gives you a graph H.
Oh, okay. The H and L is there in T.
What
This I'm saying H1 condition has H and L. Right?
is part of T?
They are part of T.
Yes.
So that.
Okay. So what basically I want to do is that, suppose I want to give a reduction from click to biclick. Okay. So I have an instance G comma K, and I want to create some instance for biclick. Okay. So what I'm going to do, I said, okay, fine. I have my T. So G had n vertices, suppose. K, L, and what else I say? H. And I want to do something interesting here. So what should I set up to get my things here? What should, like, I want a reduction, right? I want a reduction, right? Okay. So look, but S is very specific here. S is K choose 2, right? I'm not able to guarantee everything, but this I'm able to guarantee for K choose 2 sized object. Okay, but that's okay. Okay, so K prime I'm going to set equal to S, which is K choose 2. H I'm going to set K choose 2. L I'm going to set K choose 2 minus 1. Okay, now I'm telling you that we are done. With this settings of parameter, we are done. Why? If G has a K click, right? If G has a K click, then look what happens. Then there exists an X in L of K choose 2 such that it has at least how many neighbors? Common neighbors? K choose 2 common neighbors. Right? So I'm getting a complete bipartite graph on K choose 2 vertices.
show that T has some parameterized size. It's like
It's polynomial time. In polynomial time, I'm constructing.
we are constructing its but then you are using T as the input size, right?
So like everything is
So
polynomial.
G, T, oh,
Everything is polynomial. Don't worry. The whole construction is polynomial time. Up like I haven't said anything. I'll just specify if it comes. Okay. So if I set this and get this, are we done with the construction? Are we done with the reduction? Right? Because if G does not have a k clique, then the number of common neighborhood is at most k choose 2 minus 1. So I cannot get it like I cannot get k choose 2 and k choose 2 here, right? So this is exactly what it is. So this is how we are going to use this theorem for, okay? But unfortunately for us, it is this strong threshold property. Designing a graphs with strong threshold property is very hard. Okay, but I wanted to give you a flavor of the kind of arguments which are coming, which is very similar or identical to this, and will prove. Proof of this lemma is the classroom exercise. Once I told you what threshold property I like to do, what is the hard part of the whole heart is the construction of such property. Okay, which is also not very hard in retrospect. Okay, so is all clear? Okay, so now that I have defined you what my plan is and how we are going to attack the whole thing, okay, so let me drop the notion of strong. So I'm going to tolerate just threshold property. So for every nk and this and a bipartite graph T U union B with okay, so basically what I'm going to say that look, you're demanding too much, okay, so this will remain the way it is, but now what we are going to say that look, because ultimately we need certain interesting properties here. So what we are going to say that look, A will be divided into n equal n parts, okay, A will be partitioned into V1 disjoint union Vn, right? So somehow we will superimpose this. So A will be divided into this and we will demand that look, I don't care that for all x in A choose k, this happens. But we will demand little bit less. We will say for every k sized indexes there is, so look now, so V1 to Vn. Now I will have a notion of index I subset of n choose k. Right? So it's like I cannot satisfy this property. Imagine that I have a cloud of vertices here. In each, this is like V1. So this is not one vertex, but lots of vertices. V2, lots of vertices. V3, lots of vertices. Right? So now you gave me an index. N choose k. Say, hey, you said 1, 2, 3. So index is 1, 2, 3. Then I will tell you that I can find you a vertex in index, a vertex in V1, a vertex in V2 and a vertex in V3 which has this beautiful property. You give me another index, say 2, 3, 7. I will say, hey, I still can give you a vertex in class 2, a vertex in class 3 and vertex in class 7 which satisfy this property. So for different index, I have given myself a slightly more room that I can give you different vertex to satisfy this property. But here, if some vertex 2 is part of all sets in which he is part of, he is the one who has to supply the neighborhood property. But now I said when you say okay, index 2, I have lots of vertex, right? And any one of those vertex could take care of this. So in that sense, we have relaxed this condition. They say, hey, now it's like if I need to give you a common neighborhood property, I don't have one candidate, I have n candidate. For each Vi will be of certain size, V2 will be of some size, V3 will be of some size, and Vn will be of some size, right? So given any index of k size, I will tell you there exists a vertex in V1, there exists a vertex here, there exists a vertex here, which will satisfy this property. So now I have weakened it, right? I am not saying that for every x this property will hold, but for every index I will find an x which will satisfy this property. So I have slightly weakened this notion of threshold property. I'll write it down formally. Of A. What? Yes. But this n, when we will apply, this n will be exactly the number of vertex of my graph, because I will like to, oh, you are that class, you are that class.
In the reduced graph, you mean?
Yes, yes. So now I will not talk about, yes?
There exists a partition.
No, I will give you a partition. Okay? Okay. With A equal to V1 disjoint union Vn satisfies threshold property if the following holds. This is still true. I'm not going to change that condition. You give me any x in A, choose k plus 1. Number of neighborhood is this. But it's the second property which I will change. Okay, so let me write it down nicely here. For all k distinct indices, okay, I1, I2, Ik in n choose k, okay. So basically think of this as indices is nothing but a subset of 1 to n choose k. For all k distinct indices A1 this, okay, there exists x, there exists Vi1, let's call it Vi1 in Vi1 and Vik in capital Vik, okay, such that x equal to Vi1 Vik, such that x has at least how many common neighbors? H common neighbors in V. Or otherwise, in other language, T of x is greater than equal to, right? So now I have replaced this, that for all k distinct indices, I will give you a one vertex each, which will have this property. Before we said that for any x it will hold. Now for different time, if you same set, like I could be using different vertex for different indices. So maybe like if first occurs with 1, 3, 5, maybe I will use different vertex from the first class. But if you give me 1, 2 and 9, maybe I'm using a different vertex of 1, right? But given your index, I will always be able to produce this, and that is what, and this is the property, let's call this A, and this is what we will use for our proof. Okay? Okay. Now let's modify this lemma and then let's prove this lemma. Okay? Because, okay, and T, okay, we can construct a new graph H in polynomial time such that if G contains a k clique, then there exists x in this. Okay. Okay, that's all. I hope I'm not making any mistake. Yeah. Okay, that's it. I will not be like, okay. So this theorem statement, if you notice, is exactly the same. There's not much change.
The weaker assumption.
But Now we'll prove it with a weaker assumption. It's just that constructing that harder guy is very hard, and so we take a slightly weaker assumption. Okay, let's try to see a proof for this. Okay, which is actually very easy. Okay. So all of you have designed kernels, right? Especially parameterized by vertex cover, right? So how do you design a kernel parameterized by vertex cover? If you just recall, you have a vertex cover. So for example, if I was making a kernel for say Hamiltonian cycle, right? If I was making a kernel for Ham cycle parameterized by vertex cover, what is the strategy we apply? What do we do?
Now any cycle, okay, Hamiltonian cycle, then it means that it has to pass all the vertices in the independent sets also. Now,
They are equal size, imagine.
but well, that is also no, that it's not a.
It doesn't matter. Or find cycle of length greater or equal to L. If it is not a parameter, I really do not know how does it matter. So we always construct an auxiliary graph actually. And what we auxiliary graph by taking a pair of vertices from here, right? Auxiliary graph where we take pair of vertices of vertex covered. So call this C. So C cross C. And this side remains the same. And you put an edge between this vertex and this vertex if this guy is in the common neighborhood of this, because it's like routing via this. This is the most common basic strategy we always apply for most problems. Like you have a C cross C, and that is why when you apply expansion lemma or one of these things, your kernel size always bloats up by k square because this size has to be k square, right? And how do you put an edge? Okay, if I have a UV, because this is UV, and there's a W in I put if W belongs to N of U intersection N of V. This is what we do. Okay, and we're just going to do that. Okay, but slightly more smarter. And this I will leave you as a, to verify some things here, I will leave you as exercise. The guy who's making note should. Okay, so now what we are going to do, okay, I have a graph G. I have a graph G, and I have number K. All these things are there to me. But for now, all I care about that this guy has an n vertex. That's all that I care about. Now I have a T, A comma B and ET, and what is the property of A? What is the property of A? It is partition into Vn. Okay. So I will first describe a procedure. So now I have to describe what L is, what R is, what A is. So since I have already given up what my R is going to be equal to B. So R is not going to change. And what is L? That also I gave you already. It's basically tuples U comma V. Okay. For now, U comma V, and yeah, maybe let's say U not equal to V, and U is in Vi, V in some Vj, I not equal to J. So only when they are in the cross, I made this. It wouldn't matter much. Actually, no. Just let's U not equal to V. This is all that I did. I made this. Okay. And how I'm going to give an edge? Yeah. basically this is, you can think of L as like A cross A. That's all that I did, A cross A. Okay. Except that I have removed like the copy itself because U is not equal to V. That's all that I did. And how do I give edge? I told you how I will give an edge. Okay. So I will give an, so think of this as some E comma W. W is in B. If, what is E? E is some U comma V. If W is in NU intersection NV, then I make an edge. So this is my construction of my graph. But now you will ask me, come on, if this is what is the construction of graph, where did G go? Right? G has absolutely no role in this construction. So somewhere I need to introduce G into this construction. We used our nice threshold graph T for this construction, but we have not used G at all. So now let's use G. Okay. So let's call this L star. From we will make L. So this is how our L star is. We will make L from L star, and which is very easy. What is a natural way of viewing my graph, right? So what I do is that you just associate, you define a function tau from A to V of G. Assume that V of G is nothing but 1 to n. Okay. For this thing, what is the property you want? That each Vi just maps to one of the vertex. That's all that it is. What is the property of tau? Is a mapping from A to vertex set of G with the following property. Okay. For all U comma V in Vi, tau of U is equal to tau of V. Some Vj tau of U equal to tau of V. So if they are in the same class, they map to the same vertex. Right? Okay. And notice, and if I also should probably say that the map is surjective. Right? It means every vertex has an image. That's all that I want to say. Okay, fine. So we'll work with this function tau. So now how should we make L star? How do we make L from L star? Well, I have a two vertex, I have an edge in my graph. I have an edge in my graph, right? So if I have an edge in my graph, so when I go back to my inverse, the edge of vertex Vi, the edge of vertex Vj, right? What should I do there? Like, should I leave all these guys or should I remove someone?
So is A, are you partitioning A into V1 till Vn?
What?
In the first thing, A is equal to V1 disjoint of Vn.
That's part of my input.
But then you set Vg is 1 till n. Let's change this symbol, maybe last symbol.
Why?
You take A, vertices of A, and then map it into 1.
Vertex of A is a partition into V1 to Vn. There are many more vertices. I am just calling the vertex set of G as 1 to n.
Okay, so you're
Okay.
actually mapping from partition of A.
Okay. So now let me define what L star is. Basically, all I am saying that, okay, I am a pair UV. Let's make my image and C in G. Is that an edge? Look, I am a pair here, UV, in my currently, look at L star, I am UV, right? I am a vertex, right? So I say, okay, let me take image of U in my graph. I go there. Let me take image of V, let me go back to my graph.
In G.
In G, of course, then, right? Now, is that from an edge? Yes, then I keep this vertex, else I delete this vertex. So now, this is how, so basically you can think of this that on this L I have projected, basically you can think of this L contains basically edge, right? Basically several copies of edges, because if there is a Vi and Vj such that their I and j has an edge, then every vertex in Vi and every vertex in Vj, right, like that cross is there present. That's all that is happening. Okay. So now what will we say? Let's say, so let's change the definition. So this is what happens. So you have everything. Now this is how you are copying. This is how you are keeping. This is where the G comes, right? And you will see in a minute how we will use it. So what is this? U is not equal to V. Okay. Right. Now I don't need to say anything. Okay. All I will say here is that U1, U2 is in A. U comma V is in A. And what is this? Now we do not need, because edges will take care of it. I'll write in a minute. Tau out E is in H set of J. This automatically takes care of any kind of disambiguity. If I am a singleton, I don't have edge because every part goes to a different. Okay. Right? Right? So this will automatically take care of all the discrepancy which way. And this is the end of my construction. Okay? And this has all the property H1 and H2. Okay? So I'm going to prove H1 and I'll leave H2 as an exercise. Okay? Because it is like a 3-line exercise. Okay. Everybody has done this homework. Okay? Okay. So now suppose G contains a K clique. If G contains a K clique, then what is it meaning? If G contains a K clique, then I have to show X is in L, choose S, blah blah blah. Okay. Okay. I have written everything. So those vertices, this is why I use 1 to n. Now these vertices, think of them as an I, as an index set. Think of them as an index set. Okay. If I think of them as an index set, then I will get some k vertices from here, such that their neighborhood has some property. Agreed? Okay. So let's look at those vertices. Right? In T. Right? Because this is in T. But now look at all the pairs between them. Those pairs are surviving in my graph because those pairs have an edge in my clique. Okay. So let's go slowly. Okay. I mean, we'll prove it. It's not something. It's not some rocket science. But the question is, what part should I rub? Okay. Since I will not prove H2 to you, so let me just rub that H2 because it is exactly the analogous argument. And let me do this H1 for you in a simple. Okay. So how does the argument goes? Okay. It is slightly more. Okay. So now suppose G contains a K clique. Okay. If it contains a K clique without loss of generality, it does not matter. Okay. Without loss of generality, let's assume that this is 1 to K. Like it could have been anything. It doesn't matter, right? Let's call this index set I. Okay. Now by the threshold property of my bipartite graph, what does it tells us? T2. For all k distinct indices n choose k, there exists V1, V2, blah, such that blah happens. Okay. So let's x equal to V1, V2, Vk, where V1 is in capital V1, V2 is in capital V2, Vk. And what is the property of them? The property of them is that neighborhood of x is how much? H. Okay. Agreed? Okay. Now look at all tuples of V1 to Vk in L. Okay. So now I am going to define, okay, x star is nothing but Vi Vj, Vi not equal to Vj, right? And Vi comma Vj in x.
Wait, just a minute. So how that tau of that gamma of x, the common neighborhood of this v1, v2, vk. Why? No, that is fine. Why that is H? Because it satisfies.
For all k distinct edges, there exists one vertex in this.
Oh, okay. Because of this T2. Okay, fine.
Okay, so I have found this. Now let's look at X star. Yeah. So what is the size of X star? It's k choose 2, right? So this exists, and all I have to show that in tau h of x, it's greater than or equal to h. But what are the property of these guys? For all these pairs, what is the property? That hey, all of them have basically, if you look at think of a graph wise, what does this tells us? It tells us that basically if I look at my graph a comma b, look at a graph a comma b, here you have x and here you have a set of guys so that you have a complete bipartite graph between them, right? And what is the size of this guy? Is h. Okay, right? So now if I take any pair here, there is an edge between this guy and this guy for every pair here, because that is how we are constructing this edges. So all I needed to ensure is that, hey, is that edge even present there in your L at all, right? Because in L you only contain those edges which are mirror image of your edges in your original graph. But because X is a click in my original graph, there is an edge between every pair of these vertices, every index here, right? So if there is an edge between every index here, then there is an edge between every vertex of this class and every vertex of this class, right? So because there is an edge between 1 and 2, there is an edge, there is all those guys are present here. Basically V1 cross V2, all pairs tuples are present here in L. Because what is the definition? Look at any tuple here. This is in A, and tau u comma tau v is in EG. So where will the tau u will map this guy to? 1, where this guy will map to? 2, and there is an edge, right? Because that's a click. So for any pair here, right? I have an index C comma v. You look very confused, Rohani. Okay, let's go slowly.
This one thing.
G has a k click.
Yeah, okay.
So I have 1 to k. Suppose this click is 1 to k.
Just before that, when we are doing a reduction from click to biclick.
Yes.
Okay, suppose I do it when I'm even doing it. I mean, for me, I think the click to biclick direction is should be easier, right? If you have a click, then you can get a biclick. Suppose I do this reduction. Maybe I'm going off track. So the reduction is you take 2 copies of G.
Yes.
And
Think about it.
No, yeah. I'm saying the backward direction.
Please think about it.
Forward direction is okay, no?
Right? Forward direction has been okay for last 25 years.
No, that's what I'm saying. Exactly, that's what I'm saying. So even here, what are we saying? We're trying to prove if there is a click, then we are trying to prove there's a biclick.
No. I am proving certain neighborhood property. I'm not even making a reduction. I'm proving a particular lemma. It also had H2, which is very analogous. You do not understand that I have a graph with certain threshold properties.
Okay. H2 is the other direction.
Yes, but that doesn't show anything about biclick yet.
Yeah, because the construction is very different.
Yes. No, like it has nothing to do with biclick at this stage. Of course, it has to do a lot about biclick, but gradually. Okay, not at this point of time. Okay. Okay, all I am saying at this point of time at H1, what does H1 tells us? If G contains a k click, then there exists X in L to S such that this happens. So how do I say? I said, okay, fine. Let's start with 1 to k. Now, because now I want to apply a threshold property. What is the threshold property? It means, it says, if I think of this 1 to k as index here, then I can find a vertex V1 in class V1, a small V2 in class V2, a small vertex Vk in class Vk, right? X. And my claim is, And what is the property of this? The number of neighborhood of x is greater than or equal to h. So now let's, if you look at the graph a comma b, here is your x and they have at least h common neighborhood. So in your language you are correct. This is like whatever the size is, it is k comma h, complete bipartite graph. Okay. But now what we did, that is not the graph we are trying to argue about. We are trying to argue about the graph L. So what I said is that, okay, fine, let's define another vertex set x star, which is nothing but pair vi vj, vi not equal to vj and vi vj is in x. Okay, now I am claiming to you, I want to claim that tau h, I want to claim, what do I want to claim? That tau h, this is not tau h, of x star is greater than or equal to h, because this is what h. So this is tau of t, right? This is tau of t. What is my goal? Is to show tau h of x star is greater than or equal to h. That's my goal, right? Threshold property tells me that in t I have this property, but my whole objective is to show that in h this property holds. Okay, fine. How will we go about it? I said fine. Let's look at the x star, guys. How are we giving an edge? Look, how are we giving an edge? So we are saying that, hey, pick a tuple, those are my vertex set in L, and if they have a common neighbor, then put an edge between them. Put an edge between this tuple and this vertex. So for every pair here and every vertex here, right, there is an edge in my graph. So if I was talking that L star which I was talking in the beginning, clearly by definition all the vertex here into this. So remember, before I made L, I had a L star for every pair. If this property holds, make this. So in L star, basically what happens in L star, that you have k choose 2 comma h. But okay, fine. I want to say that in the L star graph which I had constructed, right, in that all this pair survives. How does this pair survives? What did we say? We say, hey, look at a tuple, look at their image. If they form an edge, then you keep this tuple, otherwise delete this tuple. This is what we did. Now for every pair vi vj, let's see if this tuple survives or not. Okay, so I go to vi vj, they are in A, clearly. I apply the image. If I apply the image, what will I get? I will get some I comma j in my original graph. And if I get an original graph that was a click, it means there is an edge. If there is an edge, it means that tuple survives. It means, and that is true about every pair there. And if it is true about every pair there, it means this happens. Okay, so that's all that we prove. So this is what H1 is. Okay, now try to prove H2. Proof is not much. It's 3 lines. Okay, it's not really much, but it's a good exercise. It's exactly like this. So you now you have to use T1 and you will be able to argue. Okay, on purpose. I mean, if you cannot do it, I can do it next time. But on purpose, I do not want to do it because it's just to get a hang of how to play with these things. Okay, but in your lecture note, this should be there. And this is how you look. You should not go and copy from the paper. You cannot see this. You cannot see this paper. It's a.
1 second, where are we using that property of tau?
What is, there's no property of it. Tau is just a mapping to
Between every two, in the same part, the tau should be same, right? That are we using somewhere?
yes, to recognize. Think of this way, that like a part is recognized with a vertex, right? A part is recognized with a vertex, and it's like when this guy is forming a click with some other guy, maybe I'm using some other vertex of that part to realize this, and that is where we are using it.
Yeah, just to clarify one more thing. So how do we construct T? Does
What?
it B from the graph G?
T has a comma b comma et.
How do we construct T is something we haven't talked about yet.
Now, yeah, right.
You had a T or a problem with b.
Yeah, how do we construct T over now one?
To T that I have not even talked about. That's whole. That is. I mean that's.
Okay, we're coming to that. Okay.
I mean that is what the point is. But first, like I just tell you some technical lemma in the beginning without any motivation. There's absolutely no utility of it, right? So now you're at least motivated to know why T could be useful, but not yet. I will not give you tea today, whatever you like. Yes. Okay? Okay. So now what I want to tell you is that, okay, so suppose, so this lemma is given to me, and suppose we are, so basically we will have a construction, okay? So there are two construction, a deterministic construction and a randomized construction. Randomized construction is very simple for T, but analysis is bit tedious, but not tedious enough. I mean, we have done way more tedious things in our MFCS course, okay? That was very good that I taught that course, okay? Because otherwise it only took 4 hours, otherwise it would have taken 14 hours to go through all those mess. Okay, so
The randomized construction, even for the stronger thing,
it doesn't exist. I mean, like,
it doesn't exist.
I mean, like, no, people don't know that it exists or not exists, but like the phenomena at which the threshold happens, people are not able to calculate it. Okay, so suppose here's I'm going to write a deterministic construction, what I will construct, and once you have the deterministic construction, what can you get from there? Okay, and then let's okay, all is well. Okay, fine. So this was the proof for this part, H1. I can only give you flavor of arguments which are here. Like really, if you have to understand it completely, which I'm still trying to digest it to my best of my abilities, you will have to read it also yourself. Like I have just told you what it is, I have broken it down. Go back and look at the paper, you will be able to follow it much more easily because you have seen an argument once in the class. Okay, so what is a deterministic construction? Which I will come maybe quite late because first I will teach you randomized construction, which is easier to grasp than playing around with Wales inequality or something like that. But suppose so what is the lemma about deterministic construction of such objects is? Okay, what does it mean that okay we will be able to construct, and you will see how much slag or how much gap is in the construction. Given a graph G on n vertices, and a positive integer k, such that six divides k plus 1 in some condition, and n to the power 6 divided by k plus 1, I have no idea from where this comes, but it comes, is greater than or equal to k plus 1 factorial, and this is fine. I mean, you can achieve these things because otherwise, if like, because for the graphs which are a function of k, the problem is FPT, so you do not care about those graphs anyway, right? So you only care about the graph when it is larger than any function of k, right? Then this is k plus 1 factorial, please. Then we can construct a bipartite graph in polynomial time such that here is soundness. What is the soundness? If G contains k click, then there are S vertices in L with at least n divided by 6k plus 1 common neighbors. Common neighbors in R. Completeness. There's a reason why I'm writing in terms of soundness and completeness, because just get used to build for FPT approximation.
This is 6 divides k plus 1.
Yes, 6 divides k plus 1. Okay. If G contains no k click, okay, okay, k click, then any S vertices in L have at most k plus 1 factorial common neighbors in R. And what is here S? Your guess? S is nothing but k choose 2. Okay? So this is what the deterministic construction means. So if you will give me a graph G on n vertices and a positive integer k which satisfy this property, then I will construct you this bipartite graph.
This is not a construction of so you're giving a direct reduction.
In there, yes. Or did I miss something in between? I missed something in between. That is, no, this is not deterministic. You are right. This is a reduction. Okay, I didn't write the deterministic construction. Sorry. Okay, this is a reduction. This is the main theorem. This is not deterministic construction. Okay, so what is a construction? Okay, I will tell you in a minute. Okay.
So in the lemma,
Yes.
G need not be bipartite. That lemma, which we proved, we really didn't use the fact.
No, G is not. G does not have to be. No. If G could be anything. Does everybody have a copy of this? Can I drop this if you don't mind? Look, the point is we are giving a reduction from click, so G could be anything. Okay, sorry. This is a lemma about deterministic construction. I was also confused. For all k comma n in n plus with k equal to 6l minus 1, I don't know why, for some l in natural numbers, okay, and n is greater than equal to this is where all this mess comes, I guess, k plus 1 factorial for all with k equal this, a bipartite graph T A union B comma E with A equal to V1 Vn satisfying the n k k plus 1 factorial n plus 1 6k plus 1 threshold property with vertex set of T equal to some order n6 can be constructed in order n to the power T. Okay, so this is a deterministic construction. What?
Is it for a fixed h at n? Because you are fixing your h to be k plus 1 factorial.
Yes. So if you give me k and n, right, then I can construct this. I'm not able to construct for every parameter.
But the original reduction that you gave,
Which k reduction?
now having all this reduction from
That lemma,
the main reduction from click to backlick actually. Yeah, where we set the parameter h to be.
I never gave you a reduction there. But I used lots of very heavy, strong properties there to just give you a flavor, right? But notice here, this reduction lemma doesn't care about what you set k and l to be. But this is what I'm able to construct. Now let me give you a reduction to biclick.
That's it.
Right? This, right? Right?
Some sort of a gap.
Yeah. Right? So now I'll give you a real reduction. Right? Now I'll give you a real reduction. First, let me prove this lemma to you. If I have this, then how do I, if I have this deterministic construction, I have this lemma, then how do I prove this lemma?
What is the order n power what? Last
18.
18 and that is 6.
Yeah, sizes. So like, because he was asking that what is the size of T and what is this size of these things. So this is what the size is. Okay. So let's see the reduction at least. Okay, I mean, as I told you, right? It's a okay. This is very simple. Okay. So basically what we are going to do. So we are going to get this construction and apply this lemma on that construction. Right? So what I'm going to do, and a positive integer k. So I take g and k. I have this graph g and k, and I get a t from here. And what is it with what threshold property it gives me? Look, this would say I am not able to construct all like this bipartite graph for every kn. I am not able to do it. Okay, but I will still get our reduction. Don't worry about it. With n k plus 1 factorial and n plus 1 whatever it is plus 1. I get this and this and I apply this lemma on this, right, which I already proved to you. That has all these two properties, right? I already proved this because once I have this graph and this construction, that is exactly that lemma says, right? This is why S I chose as cases 2, right? Because if G contains a k clique, then there are S vertices in L, because now take this, apply this lemma. And what you are going to get then? You are going to get H L union R, comma E. Okay, maybe I should say ET. Okay, fine. And this H is what we are talking about here, right? If G contains a k clique, then there are S vertices in L with at least this many things, right? If G contains no k clique, then for any S vertices in L have at most k plus 1 factorial common neighbors in R, because I have set up my parameters like this, right? So this is exactly like greater than equal to H. So your H is this. So that comes here. Your what is NKL low was k plus 1 factorial. This. So the way I remember nk, L is low, H is high. So it's like low and high, right? So nk, L, H. Okay, so this is it. Now how you give, so suppose this is what, so if I have this deterministic construction and if I have this lemma, then I have this lemma. Now if I have this lemma, then how do I prove that biclic is W1 hard? Okay, so let's prove that biclic is W1 hard. What's the big deal? You look too confused. Okay, so now we don't need this lemma for showing this. Okay, this lemma has served its purpose, so I'm rubbing this. Okay, so now I want to prove this. So what will we do? I have a G comma K and I want to create here a biclic instance. What should I do? First of all, let's take a new click star instance. Okay, G comma K 6 divides K plus 1. How does it matter? I mean, really, I mean, and Vg equal to n. We'll not give a reduction from click, but we'll give a reduction from click star, which is also W1 hard. Vg equal to n, right? And n to the power 6k plus 1, k plus 1, right? Right. Is greater than or equal to k plus 1 factorial. If click is hard, even this is hard, right? How? Look, think about it. If 6 does not divide k plus 1, add some bunch of 4 or 5 vertex, because it's like modulo something, you add some universal 4 or 5 vertex, make it adjacent to everybody, and that will satisfy all the properties. Okay, so I'm not going into this. And okay, so now let's give a reduction. This is an instance of okay.
That n power 6 by k plus 1, is that n power or n plus 1? I think it's okay.
What?
That n power 6 by k plus 1, here in this lemma it is n plus 1, but I think we got to
Oh, actually, I think you want GK to peak star.
No, it's like this is an instance of this. Okay.
Oh, this is
Okay. So what I do? So I have to give this, right? So given G comma K with this property, all this property, right? What is the property of G comma K? 6 divides this and this property holds, right? I construct H L union R comma A, right? Which has all this beautiful property. Okay. So first I'm going to construct, this is not the real instance, okay? So here is H L union R. So I'm going to call this for undisclosed region, let's call it H comma A, okay? But it has certain properties which is satisfied with. I'm going to set T as k plus 1 factorial plus 1, okay? Some number. T is not anywhere. I have fixed this, okay? So how does this look like? What I'm going to do now, I have L, I have R. This is a bipartite graph. What I do is that I take T minus S vertices here. How many? T minus S vertices. here and make it adjacent to everybody. There's a complete bipartite graph here. Okay? I will tell you why. See, I can only guarantee that S people have some threshold property, right? But look at here. I can say some k plus 1 factorial, like at most it has k plus 1 factorial common neighbors, right? And what I will do now, so this is my H star graph, okay? This is my H star graph. And what is my parameter? K star is k plus 1 factorial.
So even without doing this,
No, what am I saying?
plus
Plus 1. Which is basically t.
so what was the need of this? So because if you have that parameter, you just go by that lemma.
Then we will not get ktt.
Oh, you can't find
Gap. There
KST.
is some gap there, so you're filling it with.
With this. That's it. There's no other reason.
I mean, okay, suppose I was interested in finding KST.
Then it's okay.
That is fine. So it's only because the bicyclic is a complete.
Both sides are.
are the same.
Yes. I'm just doing some vacuous reduction. Okay. Now if G has a k click, okay, G has a k click, right? Then, I mean, if G has a k click, then there are S vertices here, k choose T vertices here, which has lots of common neighbors, more than how much? K plus 1, strictly more than k plus 1 factorial. So they have at least k plus 1 factorial plus 1 common neighbor here. You put them here, you got your ktt. Agreed? Because look at the first property, it says that I can find here a S size object who has much more neighborhood, right? What is the size of this neighborhood? K plus 1 factorial plus 1 for sure, at least. Now take this, and this is a common neighborhood. Now take this and this blub, that gives you a ktt. Agreed? Right? Just choose exactly that many number and you get your answer. Fine. Okay. Now we have to show, suppose G, if this guy has, now like normal, if it had kt comma t, then how many vertices can you get it from here? If you had a ktt here, yes, but does that imply that you have some click or non-click? So this is how you cannot use this argument. So what you say, if G contains no k click, then we have to show, right, if G contains no k click, then we have to show that it does not have ktt. That's all that we have to show. So never try that way, like in this kind of reduction, it becomes very messy. So let's use this, because we have proved, this is why we prove. So G does not contain k click, then we have to show that it does not contain ktt, and we will be done. So what we know, G does not have k click, this we know. Let's assume that G does not have k click. Okay, if G does not have a k click, what does it implies? And suppose H has ktt. What does it imply? I can only get S minus T from here. Then I have S guy here.
We don't even have to go there, right? T, right? So we can't have anything that has.
So there are at least you are picking S vertex from here. And with what is the property of those S vertices? They have at least T common neighborhood. But that's contradiction, because if G contains no click, then any S guys had at most k plus 1 factorial as a common neighborhood, and that's your contradiction. Because what did you say? Look, so suppose not H has ktt, that implies there exist S vertices in old L such that neighborhood of what is that called? There are these S vertices, say S is greater than or equal to how much? T. And that's contradiction because because our assumption is that they only have k plus 1 factorial common neighbors, right? And T is exactly what I said is k plus 1 factorial plus 1. That's a contradiction. So once you have created a gap, use that to prove your theorem. Not suppose this has, then you might get into a trouble. That is why you prove these kind of things, right? So it's exactly the same thing, but it's just that model of thinking just changes. Okay, so what I will do with this, at least I have given you how the proof overall fits into. So we discussed about the threshold property. If we have a threshold property, we can show some interesting lemmas, and by which we can show that the problem is W1 hard. Okay, so what remains to show is a deterministic construction and a randomized construction. On Friday, I'll give you a randomized construction, and the class following that, I'll give you a deterministic construction. So that's the plan, and then we will be done with showing k by click is W1 hard. Okay, what are the open questions? Notice here, in this deterministic construction, whatever this deterministic construction, where did the k bend? Okay. So what is a blow up? It's like k to k power k, right? So if I was assuming ETH and say that click cannot be solved in n to the power little of k, then what will that imply for the biclick? That you cannot have n to the power little of log k, f of k times n to the power little of log k, and that's too embarrassing. So there could be a better deterministic construction for this, and that's an open problem. Okay, and then once we have seen this construction, we will apply this exactly the same construction to show why dominating set does not have a constant factor approximation in FPT time, and that's it. Okay, thanks.